mentorship program contains the second unit on Introduction to Fracture Mechanics. Is having following subtopics like Introduction, Fracture Mechanics, Stress Intensity Factor, Corrective Plasticity, Fracture Toughness, and RCAR. Previous videos already covered Introduction, Fracture Mechanics, Stress Intensity Factor, Corrective Plasticity. Now, in this video, we'll look into fracture toughness and RCAR. So basically, the fracture toughness is similar to ultimate strength of static properties of material. When the operating stress reaches the ultimate strength of the material, the failure occurs. In a similar way, when structure contains crack, it propagates as soon as it reaches its critical value, which is known as fracture toughness. Then failure occurs. So basically, it says how long the existing crack will grow until the specimen fails. So fracture toughness, strength as well as crack length relations for any geometry of the body and loading condition can be obtained by equating the stress intensity factor K to the fracture toughness to the material, which is a function of lower geometry crack length equal to Kc. So it forms a triangular relationship between loading, fracture toughness, and the defect size. Through relation K1C is equal to sigma C square root by A. If a plate with a crack of known size is pulled to fracture in a tensile machine, the failure stress can be calculated based on the fracture load. Therefore, it follows the critical value of the stress intensity factor at the moment of failure is given by K1C equal to alpha sigma applied square root pi A, where K1C is the critical stress intensity factor for plane strength condition in mode 1 failure. A is the critical crack length in infinite plate. Sigma applied is the applied stress. And alpha is a parameter dependent on specimen of the crack geometry, where the parameter can be mentioned as a capital Y or beta. The critical K1C is also material parameter, as the same value will be obtained if another specimen of the same material but with a different size of the crack is tested. In order to get a failure strength, then one has to use this equation sigma is equal to K1C by square root pi A. So for any given crack length, one can find out what is the failure strength. Obviously, since it is inversely proportional to the crack length, a failure strength will decreases inversely square root of crack length. In order to get a critical crack length per given stress, using the same equation, one can find out AC equal to 1 by pi K1C by sigma square of whole square. So for any given stress, one can find out what is the critical stress. And the fracture toughness varies with the thickness. As the thickness increases, your fracture toughness keeps on decreasing till to the extent where it remains constant. The thickness beyond which the fracture toughness remains constant is known as plane strain fracture toughness. This figure shows the different type of fracture failure mode when the structure is very thin, where the state of stress is plane stress, it feels like a ductile material with shear leaves. But when thickness is enough to maintain the plane strain fracture toughness, it feels like a brittle failure. In between, which is mixed mode fracture, where it will have a combination of shear leaf and flat surface. So the salient features of that variation of fracture toughness with thickness is, as the thickness increases, a greater proportion of thickness fracture in a brittle manner and fracture toughness reduces. The fracture toughness reaches a lower saturation value as the thickness is increased since the stress condition of the crack tip would tend to be entirely plane strain. The value of fracture toughness is known as the plane strain fracture toughness and is denoted by K1C. In the case of thin plates, the entire thicknesses will fracture in a ductile shear modes with fracture surface inclined to the faces of the plate and exhibit considerable necking adjacent to the fracture surface. It is observed that below certain thickness, the fracture toughness again decreases. It implies that there is an optimum thickness at which the fracture toughness is a maximum. So your fracture toughness also varies with the orientation of the structure. It's based on the grain ground direction. Therefore, it is customary to specify specimen and crack orientation by an ordered pair of grain direction symbols. The first letter designates the grain direction normal to the crack plane. And the second letter designates the grain direction parallel to the fracture plane. The flat sections of various products, for example, plate, extrusion, purging, resistor, in which the three grain directions are designated L, longitudinal, T, transverse, and S are transverse. Therefore, there are six principal fracture path directions. They are LT, LS, TL, TS, SL, and ST. Now we'll discuss about R curve. When a cracked component is loaded progressively under plane stress condition, like a thin structure, the crack extends by stable tearing until such a time that the fracture toughness of the material is exceeded. The R curve characterizes the resistance of fracture of a material during slow and stable crack propagation as the plastic zone grows as the crack extends from the surface. An R curve is a graphical presentation of the resistance to the crack propagation R versus crack length delta A, not with respect to A. That's why the R curve is independent of crack length. The R curve is a plot of stress and effector versus effective crack extension. It is derived experimentally by monitoring the applied load and the application of the crack length in the component during testing. The effect of crack extension includes stable crack growth, delta A. So the region beyond the nonlinear region is now the slow and stable crack growth. That means if when crack is propagating under the load, if load is held for a momentarily, the crack also will be stopped. But beyond which, the energy release will be more than the observation, so the failure will take place.